Okay, so if we're going to look at the different anthropogenic greenhouse gases, we're going to look at two main things: where they come from, where the major sources, and then how much is in the atmosphere, and then their lifetime. So we really have, I guess we'll just write this out, the main impact. So if we look at the impacts of greenhouse gases, we really have a couple different things that we look at. One is concentration. So how much of this is in the atmosphere? That's big. Two, we look at its ability to absorb IR radiation. So it turns out that some of these greenhouse gases are much better at absorbing the IR radiation, and we won't get into exactly why, but they have a larger contribution to. So another way we look at this is the contribution to global warming, or to increase contribution to the increase in global warming. Okay. And then the third thing that we'll look at is the atmospheric lifetime. And so, atmospheric lifetime. And this is once you put some of these molecules in the atmosphere, how long do they stay there? And this is really key and critical to understanding the different models and why doing things earlier than later make a big difference. Okay, so those are the three different things we'll be looking at. We're going to make a table. So we'll have a table. We'll have what greenhouse gas, anthropogenic greenhouse gas we're looking at, the major source or sources of these greenhouse gases, the atmospheric concentration. Whoa. Okay. There we go. Atmospheric concentration. And we're going to give this in parts per billion. Parts per billion. And then we're going to look at contribution to global warming. And I'm going to put lifetime there as well. I kind of ran out of room for a column, but we'll get all of it in there. So we're going to start off with the largest concentration gas that is in the greatest abundance, and that's CO2. CO2 comes from combustion. We talked about this. Combustion. It also, the CO2 can be increased by deforestation. So we can also see that we can increase it if we can't get rid of it. So the atmospheric concentration, it has gone up since I originally wrote these notes. But when I did, it's closer to 370, I believe, 370. But I have 355. The contribution to global warming, this accounts for two things. It accounts for its ability to absorb. It's actually not the best absorber of IR radiation. That goes to CFCs. But what it does have, and I'm going to do this in a different color, in blue, the lifetime of CO2 is greater than 100 years. Which means that once you have all the CO2 in the atmosphere, it takes on average, 100 years. It could be like 50 or 200, but on average, over 100 years for the CO2 to be removed. So if you're not actively removing it on its own, it's up there for a while. And then this 55 is a percent. So we have that down. So that's the reason why we do so much focus on CO2 is because its contribution to our global warming is the greatest. The next is going to be methane. So this was also something we looked at in the climate change simulator. Methane, or CH4, we get that a lot from cattle. So cattle has a big contribution um, to our global warming. And so we see that cattle, it turns out, has three stomachs, and part of their digestion process includes lots of methane farts. Um, and so that's not good. People have actually done a lot of research on cow farts and measured how much methane they release, and it's a lot. Also, rice fields, through the process of having rice fields, some of the bacteria in there can release methane as a byproduct of digestion. Landfills in the same way, byproducts. And then oil production. We talked about these refinery gases that leak out during the process. So we see that as well. The concentration is much, much less, only 1,700. You can just see how much more CO2 there's than anything else. But you'll notice so this is 15%, and the lifetime of methane is only 12 years. So here's some good news, bad news. The good news is that 12 years is not that bad. If we reduce the amount of CH4 in the atmosphere, it has a big impact. And that's why you saw that reducing CH4 in the simulation actually had one of the biggest impacts you could do. Because over a shorter time period, it can make a big difference because it goes away. What we can see also is that there is not a linear correlation between concentration and the impact. So if you look at here, we have almost like over 100,000 times more CO2, but we see that the difference in impact is actually that same difference is not shown in its contribution to global warming as a percent. So what that means is that CH4 is much, much better at absorbing IR radiation, reflecting it back on the Earth than CO2. And we'll see the same trend with CFCs. So CFCs we have mainly removed. We don't use them not removed. We have stopped putting them up in the atmosphere because we found out they were bad. So they initially were a replacement for more toxic refrigeration. So they're very good at their cooling lines for refrigeration compressor fluid. So this type of fluid needs to be very thermal stable in general, and that's actually why it is hard to remove in the atmosphere. Now this is actually even smaller, but the contribution is 10%. So again, this is 1,000 times less than CH4, but it still has a disproportionate amount. Now the thing about CFCs and the reason why they were banned is that their resident lifetime in the atmosphere is about 100 years. So the CFCs that were put up in the 60s and the 50s and the 40s are still wreaking havoc and will wreak havoc in our lifetime. So that's why they are still a factor, and that's why we're still talking about it, even though they have been banned and haven't been used much. N2O is it comes from use of fertilizer. Also through deforestation, the process of deforestation, not the product of. Nitric acid is a very common industrial chemical, and so when you make nitric acid, you release this as well. And we'll find that as much as our contributions on the personal level are very important, as much for the mentality that some things need to be changed, we find that most of the polluters and the pollutants come from industry. And so without any change at the regulatory level, it becomes very hard to make large impacts. So we have a higher atmospheric concentration, 310, but only 6%. So you can see we've ordered these by percent of contribution for global warming. And this is approximately, the lifetime is approximately 100 years as well. So again, kind of one of these longer atmospheric lifetimes. And so to kind of just summarize what we talked about here, that that these molecules, CFCs, CH4 methane, and N2O, all absorb IR radiation with greater efficiency than CO2. So that's the first kind of point. The second point is that the reason why we're not talking about these as much as CO2, so CO2 is dominant, simply because there's just so much of it. Dominant because of the amount in the atmosphere and the lifetime. So it's a problem that is big now and will continue to be a problem for the future. So this is, so just looking at the different gases, there are others you'll notice that we haven't talked about. Ozone, that's actually a positive thing. The hole in the ozone layer also had to do with atmospheric aerosols that we put into the atmosphere, but it did a different thing. So the hole in the ozone layer is actually not a part of global warming. It is still bad, and it is still caused by humans putting things in the atmosphere, but it is slightly different. So that's a summary of all the different contributions of anthropogenic greenhouse gases, specifically looking at concentration, the ability, efficiency of absorbing IR radiation, and the lifetime these gases stay in the atmosphere. And so we see that CO2 is more than half of all global warming contribution comes from CO2, though there are other gases as well. So we should know that those are also factors.